Calculus BC, we are starting the year off. We begin actually in our chapter 3, which is really the fundamentals of the derivative. And thank goodness this is something that you've learned before. Let's just take a look here at this picture in the top left corner. Let's say that you have a function f of x, okay? And this function f of x, you can see it's a curve. It's this curve in black in the first quadrant. And there are 2 points on that curve. Point P, that's where x is equal to a. And then there's point Q where the x-coordinate is just called x. So tell you what, I'm going to look at point P and I'm going to call it a, comma, f of a. I'm going to look at point Q, and if my x-coordinate is just called x, we'll have that called x, comma, f of x. So in blue, you can see you have a line connecting from P to Q. That's what we're going to call a secant line. Now, just like in geometry, a secant line would be a line that would cross a circle twice. Right? So that's what we'd call a secant line. Now, by the way, in the same chapter in geometry, you'd see if a line would just touch the circle once, it would be called a tangent line. Now, we can extend these ideas into functions where if a line were to cross a curve at 2 points in this small vicinity, in this small little area or neighborhood with x values, we would call that a secant line. Now, by the way, the line might touch the curve again. It might touch it a whole bunch of times, but just within this narrow value of x values from a to x, you can see it just touches twice. By way of comparison, we could have a tangent line would just touch the curve once. So let's look at the slope of line PQ. How did we find slope? Well, slope was always y2 minus y1 all over x2 minus x1. Always, right? That's how you find the slope of any line. So here we have our x2, y2, and here we have our x1, y1. You can see very, very quickly that f of x minus f of a is what you have in your numerator. Down below you'd have x2 minus x1, x minus a. There you have it. That's the slope of this secant line. But how could we get a tangent line out of this? Well, for this, I think I'm going to come on over here. It's not exactly the same picture, but it's something that we have here. In red is a function, right? We've got this red function that we have, and you can actually see up in Desmos where we put this together. This is actually a parabola. It could be any function, though. Look at this green line. This point that you can see the crosshairs on, this would be like point P. Up here would be point Q. This green line would be what we'd call a secant line. Now you can also see this purple line. This would have the same point P. P would be the point of tangency for that purple line. It would be where the curve would actually cross your parabola. But you might wonder if there's a connection between a secant line in green and this tangent line in purple. Well, look, if I were to take point Q, and I'm dragging it right now, you can see I still have a secant line. This green line is crossing the parabola at 2 points. But look, as I get closer and closer and closer, it begins to look like this green line is becoming the purple line. And right over here, they're one and the same, aren't they? So how in the world could we get this to happen? Well, I want you to look. This point that I grabbed, you can see the crosshairs are on it right here. We called that Q. It had an x-coordinate of x. As the x value there gets close to the x value here at P, as x gets close to A, you could see what happens. So last semester, thank goodness, you studied limits. And what's happening right here, this is what's going on for our tangent line. Our tangent line, we're going to say, hey, we're going to use the slope of that secant line. But take a look right here. This is so critical. We're going to say, as this x value approaches A, you can see point Q would come here and then closer. Pretty soon you would get that tangent line, wouldn't you? You know, and you could see what's going to be happening. So to get a tangent line, you need a limit. You need to say that as this x2 value gets close to the x1 value, as x approaches A. Now, another word about limits, I hope you remember that this notation is saying that x will approach A but not equal A. It's getting as close as you could ever possibly imagine to A, but without truly equaling it. So we still have this concept of the slope formula of y2 minus y1 over x2 minus x1. It's always that slope of a secant line of two distinct points on the curve. But as we allow that second point to approach the first point, and the limit allows us to write that as x approaches A, this is what we get for our tangent line, of course, slope, right? That's what the M means. So, wow, that is so critical. You can notice the notation. It's written as M sub A. Well, this is a valid definition of a tangent line slope, right? By the way, it's going to be the definition of the derivative. You already know that. We're going to talk about that soon enough. But as you take a look at an alternate version, wow, you can think, well, what's going on here? Take a look at your second point. You're not calling it x. You're calling it A plus H. And you could say, well, why would you want to do that? Well, you're using what you started with A, and you're saying, let's just move over a little bit. Let's add an H value to A, and we can just move on over just a little bit. Now, take a look at this. You have point P. That is still A, comma, F of A, isn't it? But look at point Q. We'd have A plus H, comma, F of A plus H. Look at that. So here's your x1, y1. Here's your x2, y2. Just a different way to write this. Instead of calling, you know, this x value just an x down here, we're calling it A plus H. Well, look what happens. You're still going to have y2 minus y1 all over x2 minus x1. You still have line PQ in blue as a secant line. Well, what's y2? Well, y2 is f of A plus H, isn't it? What's y1? Well, that's f of A. Look down below, though. Your x2 is A plus H minus, well, what's your x1? That's an A. A minus A goes away, doesn't it? And that's where you get this secant line slope, this alternate form of f of A plus H minus f of A all over H. Now, once again, you could say, well, wait a minute. How do we slide over that second point so that that second point can be approaching our first x value there? That A plus H can be sliding over to A. Well, you can see we're not even using x in this expression at all right now, are we? Everything is in terms of A and H. You could say, well, what happens as A plus H gets closer and closer and closer to A? Well, I hope you can see that that really means H is going to 0. Now, once again, we use the exact same setup for the slope of the secant line. But when we say the limit as H approaches 0, what we're saying is this point Q is going to get closer and closer and closer and closer and closer to P, like I showed you on that Desmos demonstration, that A plus HX value is getting closer and closer and closer to A. So points P and Q are getting super close together. That's how you can form a tangent line. Well, I think you guys have probably seen already that this alternate form shows up a lot. It shows up extensively. It really, really does. So, tell you what, let's actually use that right here to help us out. It says, let's let f equal radical x, and let a be any real number greater than or equal to 0. Can we find the slope of the tangent line of f at a radical a? Well, absolutely we can. Let's just realize that that slope is going to be the limit as h approaches 0 of f of a plus h minus f of a all over h. Well, what's f of a plus h? Well, guys, I hope you know function notation is kind of like saying f of a blank equals radical blank. So in other words, whatever you put in this parenthesis, you'd put into this other parenthesis right here. So when I say f of a plus h, that's going to be radical a plus h, isn't it? And forgive me, don't forget your limit. That's super important. If you did that, that's not right. The limit is definitely talking about how h is going to be approaching something, and if you lose that, you've lost the whole concept of the problem. Now, f of a, of course, is just going to be radical a, and then down below we'll just have an h. So right now, guys, as we're looking at this, you could plug in your h going to 0. I know I just said that really in a limit, h really won't equal 0. That is true. But, since we're getting so incredibly close, the closest we could ever truly get to h equaling 0, it would be okay to plug that in to see what we're getting close to. And this would become a radical a plus 0 inside of, this square root. It's a plus 0. It's just radical a. So radical a minus radical a, that's 0. H is 0. Guys, you'd have that very troubling 0 over 0. Never, ever, ever write a final answer of 0 over 0. That's indeterminate. What we are in need of, though, is trying to work things out. I hope you remember some basic ideas of algebra, that when you have an a minus b, when you multiply by the conjugate a plus b, you'll get a difference of squares. Now you might say, why in the world would we ever want to do that? Well, squaring, getting squares over here, is going to get rid of square roots. So that actually is a wonderful idea. How about I just multiply by the conjugate of what we have up on top? And of course, really I want to just multiply by the exact same thing down below, so that I'm really multiplying by 1. And when you multiply any fraction by 1, guys, you won't change the value of that original fraction. So we've got this limit as h goes to 0. And look, we'll have a squared minus b squared. Well, here's your a, capital A, minus a b, and here's your capital A plus b. That's the way you want to think about it. What's a squared? Well, that's just going to be a plus h, which is just lovely. What's your b squared? Well, that's your radical a. When you square it, you just have that a. Now down below, don't lose sight that you've got this big mess down here, don't you? Now, here's the really cool part. Why'd you do this? Well, now you're going to get a and a minus a are going to cancel out, right? And even better still, look at this. You've got a 1h and an h down here. That h up on top is going to cancel with this h down below. So, really what we have, I'm just going to write this out a little bit more. We've got this limit as h goes to 0 of 1 all over, well, we'd have this radical a plus h plus radical a. And you could see you really are going to wind up with down below radical A plus radical A, which is going to be, a 1 over 2 radical A. Okay, so what are we really seeing here? This tangent line slope is actually 1 over 2 radical A when you've got an x value of A. Okay, so that's wonderful. You've just found a tangent line slope. Well, now they're going to go a little bit more into writing the equation of a tangent line. And this tangent line at 9, 3, well, you now know that A would equal 9. And how do you know that? Well, look at this. It's A radical A. That's what any point on that curve would look like. So you've got that information out there for you. Well, can you write the equation of a tangent line? Guys, I'll tell you what. First of all, you can always go to point slope to do this. Right? You've got this thing right here. And, you know a point, x1, you know a point with a y value also, that's x1, y1, that's 9 and 3. All you've got to do is figure out what that tangent line slope is. So here's the cool thing. We can say the slope of that tangent is 1 over 2 radical 9. Radical 9 is 3. 3 times 2 is 6, so it's 1 over 6. So look at this. We could write y minus 3 equals 1 over 6 times x minus 9. That's an equation of a tangent line. By the way, you can write that as a final answer. Lately, what's been happening too is the College Board has just been adding a 3, like bringing that other term over. Actually, and you'll see this on AP Classroom, you'll see a lot of answers written this way too. So I just want to prepare you for how you'll see a ton of answers from the College Board being expressed. Okay, but point slope is actually awarded is proper work too. So I hope this is going well for you. The bottom line is you guys already know there is a shortcut to get the slope of a tangent line. That's the derivative, isn't it? So tell you what, for the sake of time is so precious right now, we're going to skip the bottom of this first page, just streamlining it a little bit. Trust me, you're going to be okay. What we're seeing is just in a rough, quick description here. You can find an average rate of change between 2 times. The closer your 2 times get to each other, you're actually getting closer to approximating the instantaneous rate of change, the instantaneous velocity. And so, you can definitely begin to see how that ties into the picture here. If your x values were time, for example, the closer your times are to each other, the closer your approximation to a tangent line is. And if you wanted to really get, let's go to page 2, what the true instantaneous velocity is, you'd need a limit. Now, this right here is a very important definition that you're going to see so much in physics and in calculus. We start with a position function. Maybe that's going to be a position in feet, and maybe time is in seconds. I think you're going to see that in just a little bit. You might wonder, is there a way that we could get an instantaneous velocity? Guys, this sure looks like a tangent line slope. It is. You could see as our times would get squeezed closer and closer together, and that's what that limit is going to do in this position function. You're going to be able to come up with the derivative of the position function, which is the instantaneous velocity. It's change in position with respect to time. So here's what's going on. Let's just say for question 2, Mel drops a football from a blimp 600 feet above the ground. The function s is given to us. T is in seconds. The position s is going to be in feet. And you can see already at t equals 0, if you plugged in t equals 0, it would tell you that the initial height of that football would be 600 feet. They want you to find the velocity. Well, of course, we could go back to the limit definition. What we're actually going to do is come back here, right? Of course, it's really right over here. That's what it ultimately is doing, right? We're just putting that application into context. Guys, time is so critical. We're not going to do a limit definition for every one of these beginning problems. You already know this shortcut. So, tell you what, I'm going to do the following. I'm going to say S prime of t equals v of t. What's the shortcut? Well, you guys should know this. Take your power of 2, drop it down. You'd get negative 32t. What's the derivative of a constant of 600? Well, it's 0. There it is. So what's v of a? For any a seconds, you would have this for your instantaneous velocity. An immediate note is that it's negative. Guys, when velocity is negative, velocity we're going to learn later on, it's actually a vector. It will give us not only a magnitude or a quantity, but it also gives us a direction. And the fact that this is negative indicates that the ball is traveling down. We're also going to have the context of traveling right and left before too long in this chapter. And, you know, when we get to that, if velocity is negative, that indicates you're traveling to the left. And you'll need to know that in physics as well. Well, let's take a look at B. At t equals 3 seconds, well, you'd say v of 3, that's negative 32 of 3. That's negative 96. Negative 96 what, though? Well, it's feet per second, right? Look up here in yellow again, up in this definition. S is in feet. You know, your x coordinates are measured in seconds. So your slope, guys, the units of your slope will tell you something. Units are so critical. You're going to hear me constantly reminding you about how the College Board on the big AP exam, they will actually mercilessly take off a point if you don't have correct units in certain situations. So, wow, we definitely need to know how to do this. Well, let's follow up with part C. When the ball hits the ground. Wow, when the ball hits the ground, let's think about this for a moment. When the ball hits the ground, the position, S, will be 0. So let's go ahead and say 0 is equal to negative 16t squared plus 600. Let's add a 16t squared over here. Let's divide by a 16. And this is where, hey, you know, you can get your calculator out. I hope you can definitely work this thing out as well. You can easily do some dividing and simplifying. You know, so many different ways you can get that done. We know we're going to take a square root here too. But just throwing that out, that's 75 all over 2, isn't it? So t squared equals 75 all over 2. We're going to take square roots. And guys, please understand that as you do that, t could be positive or negative. But in this context, t won't be negative because it's dropped at time 0. So, you know, it's very important for us to be able to realize in general there would be 2 answers. Tell you what, I'll just go second answer here. Looks like it's 6.1237 or 6 point, something like that. In AP rounding, we usually only go out to 3 decimal places, but we reject the negative. So we're going to say t is equal to just the positive 6.1237. So it hits the ground at that time. Now what? Now we want to find the velocity. So we want to know the velocity at that time right here. I'm going to put a little squiggle there. Negative 32 gets multiplied to that. So I'm going to go negative 32 times second answer. And that's, and we can write this out real quick. So evidently that's negative 195.959. And don't forget your units, that would be feet per second. Okay, so it's a little bit of a thinking problem right here. First, you have to find the time when you hit the ground. Then, of course, you have to use the velocity. The bigger point I guess I want to make is simply this. There will be times when you will be asked to do the derivative with a limit. However, a lot of times, especially because time is so precious right now, we'll just jump to the shortcut a lot and work things out. So in a summary right now, we need to get to the big picture. Calculus deals with change. It's awfully difficult to try to define a course with one word, but if it were possible, you could say calculus is a study of change. That's not perfect by any means, but you will see this concept show up an unbelievable amount. Velocity that we just looked at is just one example of a rate of change. You could have all different types of rates of change, and we will see them throughout the year. As long as f of x is defined on an open interval, here's what you're going to see. The average rate of change, is this super important. What is the average rate of change? Guys, the average rate of change is the secant line slope. Plain and simply, it is y2 minus y1 over x2 minus x1. Very, very, very important for you to see that. The instantaneous rate of change, also known as the derivative, is the tangent line slope. And that, of course, will allow you to get a very quick, practical idea about the instantaneous rate of change at a particular x value. You could see the power of that when you can actually find the exact velocity of a football hitting the ground and so forth. The instantaneous rate of change is called the derivative. How do we denote it? Well, with that little tick mark there, f prime of a. Yeah, that's your tangent line slope for sure. But that's something that you can do so very, very, very fast. So let's close with example 3 really, really fast. We can use our shortcuts to help us with the derivative. The average rate of change. Well, guys, the average rate of change, look at example 3. We've got a parabola y equals 5 minus x squared. And here is this interval from 3 to 3.8. Here's your x1, here's your x2. By the way, we could say f of x is 5 minus x squared. So what exactly is going on here? Well, we're going to say y2 minus y1 all over x2 minus x1. Okay? And if you just worked this thing out as you see it, you would be just fine. So this would be 5 minus 3.8 squared minus 5 minus 3 squared. And down below we'd have our 3.8 minus 3. So this is where, tell you what, and this might get a little hard to see. Notice alpha y equals, we'll bring that up. I'm going to go parentheses and go 5 minus, I don't even need parentheses with the 3.8 squared. I'll close the parentheses here. Minus, and then here we'll go 5 minus 3 squared. And I'll let the calculator clean all that up. We'll go 3.8 minus a 3. And you can see we get negative 6.8. That is your average rate of change. Okay, that's your average rate of change. It's also your secant line slope. The instantaneous rate of change, by the way, is the derivative. Let's use the shortcut. What's the derivative of this thing? Well, derivative of 5 is 0. Derivative of negative x squared is negative 2x. And we want this at 3. We don't need a calculator here at all, do we? Plain and simple, that's negative 6. This is it. This is your instantaneous rate of change. So, that wraps up our lesson on 3.1. Lots of review, but we're really setting the stage for a lot of important work down the road. Our homework, only do the limit definition when you are asked. Otherwise, you may take derivatives with our shortcut like I just did here. Best of luck to you. Please let me know if you're having any issues or if you have any questions.